Hello! In today's Feature of the Week video, we will look behind the scenes of the computation of the lambda z parameter. It is the slope of the terminal elimination phase calculated in pkanalysis. It is used in the, for example, extrapolation to infinity of the concentration curve, and so in the calculation of pk parameters such as systematic clearance, or for example, in the calculation of the acceptance criteria that we have already seen in the previous video. Just to remind you, in pkanalysis, there is a dedicated subtab called check lambda z that shows the pk data for all individuals with the log transform concentration. The lambda z will be calculated using points that are marked here in dark blue. These points can be selected automatically with main rules that apply to all individuals, or manually for each individual independently. So let's start with the main rule that assigns the same number of points to all individuals. I have selected an option points in the main rule menu here with the last 6 data points that are going to be used to estimate lambda z. For a pk dataset, data points are pairs of measurement times and measured concentrations. Here we look log transform concentrations, so yi denotes the logarithm of measured concentrations. Ideally, for the terminal elimination phase, all of these data points would lie on one line called here y hat. It is a linear function of time with the slope equals to minus lambda z and the intercept I lambda z, which is a value of y hat at t equal to 0. However, in real life, due to measurement errors, data points, instead of being aligned, are spread around this line. And in this case, the observation y is given by the regression line y hat plus the residual term e. In this equation, values of ti and yi are fixed and known as they come from the pk dataset. The unknowns here are the slope of the regression line, lambda z, and the intercept. So we would like to optimize their values so that the regression line passes as close as possible to all data points. There are many methods to do this optimization, and one of them is the least square method, which minimizes the sum of squares of the residuals. So this is what we see here. For each individual, a line represents the linear regression that goes as close as possible to the last 6 points. Of course, if I add or remove points, the new regression line will be different, and so the values of the lambda z and intercept will be different, and it will affect the NCA results. So here I use the same number of points for all individuals. But the question is it the optimal choice? We have to consider variability between individuals and the fact that they can have different measurement times, so the final slope may start earlier or later. So here on the left, 6 points seem good to capture the terminal elimination phase, but for the individual on the right, it seems that the terminal elimination phase starts at a later time, and using only the last 4 points would capture it better. So it would be better to have a statistical tool that assesses the goodness of fit of a linear regression for different number of points that are included. One method is to look at the coefficient of determination called R-squared that is calculated for each individual independently. So to understand it better, let's look at different types of the variability of the data. The sum of squares of residuals, called here SSR, is the variability of the data with respect to a regression line y hat for a given lambda z and intercept parameters. The total sum of squares, called SST, is the variability of the data with respect to the mean value given here by the y bar and presented with the horizontal line in the plot. The coefficient of determination summarizes these two quantities and is given by the following formula. Larger values correspond to a better fit. For example, when the residuals get smaller, that is, SSR decreases, then R squared gets larger. Its maximal value is 1. The total sum of squares, SST, represents the total variation of the data. It is a sum of the residual sum of squares, SSR, and the planed sum of squares, SSE. Rewriting the formula for R squared, using it instead of the residuals, we obtain that the R squared is a ratio of the explained variability to the total variability. So in other words, it measures the amount of the variability of the log transform concentration that is explained by the independent variable, and the independent variable in this case is time. For example, R squared equal to 0.9 means that 90% of the variability in Y has been explained by the linear regression. An extension of this method is the adjusted R squared coefficient, which takes into account the number of data points used in the linear regression and favors adding more points. This is a default method in pkanalysis. So let's look again at the previous example. With this toggle here, I add the information about the adjusted R squared coefficient. Now, if instead of an equal number of points, I select the adjusted R squared as a main rule, then only the last 4 points are selected for the second individual, and it gives a better fit of the terminal elimination phase, which can be seen with the increase of the adjusted R squared coefficient. So now let's look closer at this automatic selection of data points based on the R squared or adjusted R squared method. The first thing is that during the selection, the algorithm excludes concentration with 0 values because the method uses the logarithm of the concentration, so in the case of 0 or negative values, the logarithm cannot be computed. The algorithm also excludes data before Cmax, before the end of the infusion, and the point at the Cmax for non-bolus administration. Then the algorithm calculates the goodness of fit using either the R squared or adjusted R squared. It depends on what you select. The check is for consecutive sets of data points, starting from the last 3, then the last 4, 5, etc. It is because we look for the terminal elimination phase, and we can assume that the concentrations associated with time are ordered. To compute lambda z, at least 3 points are required, and the final slope has to be negative to obtain a positive value of lambda z. In addition, if for a set with more points, the adjusted R squared does not improve, but the decrease is within the margin, 10 to the minus 4, then the algorithm estimates lambda z using the regression line with the larger number of points. Selecting a correct number of points is very important, as it can affect values of different NCA parameters. The automatic procedures are convenient, for example, when there are many individuals and the manual selection would take a very long time. However, these automated methods can be suboptimal in more complex cases or if there is a lot of variability in the data. So it is a good practice to combine these automatic methods with the visual inspection of each PK profile to assure that the interval for the terminal elimination phase has been correctly selected. Luckily, in pkanalysis, you can do it very easily with the graphical preview in the check lambda z for each PK profile, and you can add or remove points manually. If you don't know how to do it, then take a look at the feature of the week number 54, which explains all the methods in details. Thank you for listening and have a good week.